All right. Welcome back. We are moving on. The first video, we introduced the idea of a mixture distribution, and the idea is pretty simple. Just take valid distributions, apply weights that sum to 1, and you get a new, more complex distribution. So now we're going to talk about nonparametric density estimation, and the key word here is estimation. So if you're given a pile of unlabeled data, think about the picture that we started with here, where we started with a bunch of just blue dots. How do we get from that picture of just blue dots to a mixture distribution given by the colored ellipses here? How do we estimate the parameters of that distribution? So, estimation. Okay, so here's the problem that the notes are going to deal with. We've got a pretty unusual density. It's got, of course, a lot of mass, right around 3, but it sure stretches out in the negative direction a long way. So we're going to assume that these aren't some nice distribution, normal, gamma, or anything like that, and we're going to fit a mixture model to this data. So I think we mentioned this in the earlier set of notes, but any density, of course, a density function f of x has to be greater than or equal to 0 for all x. It can't take on negative values. And of course, a density over its sample space has to integrate to 1. So what we do is we can take valid densities that on their own would integrate to 1, and we can weight them, and so long as the pi's are non-negative and sum to 1, then we can get a new valid mixture density. So our model for our mixture density is going to consist of 3 pieces. The first piece is we're going to assume that each of the mixture components is normal. And this is not critical. You could plug in a different density if you like, but for our purposes, normal is going to work fine. The next piece is called the Dirichlet distribution, and this is going to be used to assign a probability distribution to the pi's, so to these weights. That distribution, of course, has to meet the conditions on those weights, and so the pi's always have to sum to 1. And the Dirichlet distribution is a distribution which has that property. A third piece of our model is going to be a categorical distribution. This is going to sort of play the role of the Bernoulli distribution in our Bernoulli beta model. It basically is going to assign the outcome to a mixture. So each of our data points are, think of those blue dots on that figure, though each of those guys has to get assigned to a mixture, and this is going to do that in a random way. Additionally, of course, we're going to have some prior distributions, but the 3 pieces that we need to think about are this normal density on the mixtures, the Dirichlet on the pi's, and the categorical, which is going to assign the data to a mixture component. Okay, so let's step through these. You're familiar with the normal, so let's jump right to the Dirichlet distribution. The Dirichlet distribution takes values on the simplex. What is the simplex? It's exactly what we need. The simplex is the set of points which sum to 1. So I think I said this in the last lecture, but let me just remind you, if k equals 3, the point 1/3, 1/3, 1/3 would be on the simplex. The point 1/2, 1/4 would be on the simplex because this sums to 1. But of course, 1/2, 1/3, 1/8, well, let's just say 1/2. This, of course, would not be on the simplex. So the Dirichlet distribution is a distribution whose support is on the simplex. And its PDF is given by this expression here, which looks complicated at first, but it's actually perhaps not as complicated as you might think, because we've seen a distribution that looks like this, and that was the beta distribution. You'll recall that the beta distribution gave us the support of the beta distribution was 0 to 1, and we used it as a prior distribution on pi when we were doing a beta binomial, or a binomial beta model. And the beta distribution had a PDF that was given by gamma of alpha plus beta over gamma alpha, gamma beta, and then it had pi to the alpha minus 1 and 1 minus pi to the beta minus 1. Well, if we look at this, that looks basically the same way. What we have is a gamma of a sum of parameters. Rather than calling them alpha and beta, we're just going to call them alpha 1, alpha 2, alpha 3, alpha 4, up to k, where k, of course, is the number of components in our mixture. In the denominator, what we have is a product of gammas. Again, these are gamma functions. The parameters are what we're interested in. So this just looks the same. And of course, what we have here is the same as what we have here. We've got a pi. You could think of this as pi 1 and pi 2. And notice, of course, pi 1 plus pi 2 sum to 1 the way that I have it written. So the Dirichlet is just an awful lot like a beta, only for more than 2 components. We will want to think of this as the kernel. Of course, the stuff out front is just a normalizing constant, and so when we go to look at the posteriors, we will probably disregard that and just focus on the kernel. Okay, we are also going to use a categorical distribution, and the categorical distribution basically assigns we're going to use it to assign a mixture model. So the way I'm going to think of it is we're going to think of Z being distributed, we're going to just call it categorical pi. And I've underlined my pi there because it's really a vector of pi's. We could think of it as categorical pi 1, pi 2, up through pi k. So what it does is basically it knows the probabilities. This is the probability of being in category 1. Here's the probability of being in category 2. Here's the probability of being in category K. And knowing those probabilities, it draws a Z, and this Z returns a 1 or a 2 or a 3 or a K. It just tells us which category it has been drawn from. Its PDF, f of Z, would be the product from little k equals 1 to capital K. Capital K is our number of categories. And then it's pi lowercase k, indicator, that's supposed to be a big fat 1. Let me try that again. Let me just write it this way. 1 indicator that Z equals K. So what is this saying? Let's say little k is, let's say Z here is 2, meaning that our random variable has takes a value in 2. What this is supposed to do is it's supposed to return the probability of that. What we have is a product of pi's where the exponent is this indicator variable. If z equals, so what's going to happen is we're going to step through the k's. So let's start with k equals 1. Does z equal k? No, it doesn't. So this exponent becomes a 0. Pi to the 0 is 1. So in my product, when k equals 1, I've got a 1. Now when k equals 2, this indicator returns a 1. I get a pi k to the 1. So I get pi k. And then when k equals 3, of course, this is 0, this is 1. And so what we end up with is pi k exactly like we want. So I think the tricky thing about this categorical variable, when I explained it up here, it probably made sense. This guy takes a value of 3 with the probability pi 3. This looks complicated, but all this is it just returns the probability that is described by up here. Okay. So I claim that the categorical Dirichlet, it turns out that this is a conjugate model. And we've actually seen this before. We said that, but we've only seen it in 2 dimensions. We would have said something like zi given pi is Bernoulli pi, and then pi was beta, alpha, beta. Here, what we're saying is you give me a vector of alphas. The Dirichlet, of course, returns the value of a random variable, really a random vector of pi's that sum to 1, and then zi would be drawn from a categorical variable with those probabilities. Okay, it turns out that this model is conjugate for pi. We will see that here briefly, and as I already said, it can be viewed as a generalization of the beta binomial. So here we are working through the full conditional. This is our Dirichlet prior. Clearly, we've got the normalizing constant. We've got the kernel of the Dirichlet prior. This is the likelihood. This part in here is the categorical density that we just wrote down. And then this, of course, is just the product over all of the observations. And we are missing, in fact, one little thing. This should be a zi. So what there's a zi. What category is the ith observation associated with? And this is keeping track of all those. So to get from line 1 to line 2, all that's happened is they've eliminated the normalizing constant. To get from line 2 to line 3, well, what's going to happen here is this guy's going to return a pi k every time zi is in category k. And this is summing over all, or multiplying over all n observations, but nk of those observations are assigned to category k. So this just simplifies to a product of pi k to the nk. It's basically just counting how many observations are in each component. And what I have here is I've got a pi k to the stuff and a pi k to the stuff, and so I can write that as pi k to the stuff plus stuff. And what we see is this looks like the kernel of a Dirichlet density. It looks like something of this form. It's just missing its normalizing constant. So what we've done is we've shown that the The Dirichlet is conjugate for the categorical random variable. So this just summarizes what we found. We found that pi given z is Dirichlet, where the probability of being in category 1 is n1 plus alpha 1. So it talks about, it's got information about how many guys are in each category, and it's got information about the priors. Okay, we said that we were going to use a mixture of Gaussian distribution. So what the categorical Dirichlet role that we were just talking about is actually going to be a prior on assigned to our mixture, and the mixture is going to be composed of Gaussian distribution. So we're going to have Gaussian bumps like we had in that cartoon figure, and we need to estimate the parameters of each of those Gaussian bumps. We need to estimate the pi's. We will select k to be the number of components in the mixture, and some components can be missing. So in practical terms, this maximum is the maximum number of components used. So we need to set a maximum number of components, but we kind of, some of the components could end up basically having zero mass. Okay, so here is the hierarchical form of our model. Our data, given that it is in component k. So this says the zi equals k tells me observation I is in component k. So if I knew that observation I was in component k, then x would be distributed normal with a mu and some sigma that describes that normal. The zi's are categorical with probability pi. The pi's are Dirichlet with hyperparameters alpha. And so these are our priors on our normal distribution up here, and we can draw from this model using a Gibbs sampler. So that's exactly what this slide says. Everything is conditionally conjugate. You can get there through a Gibbs sampler. It is pretty complicated, as you'll see in the slides to come, but this is just Gibbs. So just jumping in, I guess the full conditionals for the z's are, I think it's most easily seen here. What is this? Given mu and sigma, so assume I know the Gaussian bump, and assume I know the probability associated with the Gaussian bump. So then the probability that an individual observation comes from mixture K is given by the value of the Gaussian bump at that location divided by the sum of the values of the Gaussian bumps at all those locations. Okay, if your head is swimming about this, it's totally intuitive. Let me take you back. Sound effects important. Okay, imagine we're here. So what we're going to be doing is we're going to be doing a Gibbs sampler, and we're going to be updating the mu's, the centers, and the covariances associated with our normals. But for every step in our Gibbs sampler, we have a mu, we have a sigma. And so let's assume I want to assess the probabilities associated with the categorical variable of this one data point. What's the probability that that data point came from the black density? Basically zero, because that black density has no mass out here. The probability associated that it came from the orange mixture is essentially also 0. The red and the green at that location have about the same density values. And so what we would say is that our probabilities of this point being associated with the mixtures would be basically 0, 0, 1 half, 1 half. This point would be 0, 0, nearly 0, 1. So that's all that's happening here. If I go back to where I left off, this thing just is evaluating each of the densities at that one location and dividing by the sum of all of the densities evaluated at that location. Okay, so the next many slides are going to have code that you can run, and it will be posted on Canvas that will do this for you. I'm going to, rather than bore you to tears by going through this step by step by step, let me just try and describe this at a fairly broad level. As with all of our models, what we need to do is we need to start with some hyperparameters. So we're going to have 2,000 iterations. We are going to have a mean of 0 and a variance of variance of x. Oh, these, okay, so A and B are going to be on the inverse gamma. Oh, tau squared, variance of x. What's going on here? We have data. The data, imagine, what we have is we've got that data that looks, it's really low, and then we've got this spike here at the end. We can calculate from that data what the variance of this is. So we can use that as a prior for all of the mixture, all of the components of our mixture. And that's going to be basically uninformative because the variance of the whole thing, of all the data, is going to be larger than the variance of any of the individual mixtures. We're putting on a diffuse prior through our Dirichlet model. We're setting all of the alphas equal to 1, and so we're not going in with any prior information about which mixture is going to be more probable. This is just setting some starting values and giving us some places to store some results. This is storing results for the parameters. This will be used to plot some results after the fact. And then we get into the bulk of it. So let me slow down just a bit here. We've got this overall for loop, which is going to step us through the 2,000 iterations. But within this for loop, I've got a whole bunch of things that I need to update as I work through my Gibbs sampler. So this is basically updating the parameters associated with our Gaussian bumps. So to do that, we have to know which points are assigned to the Gaussian bump. Now you're saying, wait, I started off with these blue points. I don't know which points are assigned to the bumps. That happens in our Gibbs sampler. What we're going to do is we're going to assign all the points to a bump. We're going to and then we're going to update that every time via the correct probability, which we talked about back here. And then, so if I know the points that are in the bump, then I can if you look at this kind of section right in here, this looks like updating the mean and the variance for our normal distribution. So that's exactly what's happening. Now we're going to update component membership. So this is the probability of being in each component. These are the cluster probabilities being updated. And then here is where we're going to update those component assignments. And so this is basically sampling from a categorical with the right cluster probabilities, which we got back here. we update the probabilities and store things, construct the density function. And now what we're going to do is we're going to draw, we're going to do this 2,000 times. Each time gives us a realization of our mixture density. And so this figure here shows 50 realizations of that mixture density. And you can see that it seems to get it pretty right. We've got three pieces. We've got a bump here, and of course the tall spike there. You can see that there's some variability a little bit around here, but overall this is a nice flexible model which captures this overall density. Here we ended up only using 3 components. This says many observations move between components in each iteration, while some tend to stay in one component. So this is just asking how many of our points are jumping around. And this is, actually, this is how many times do they, over the course of our iterations, how many times do they switch? So this is trying to just show you a little bit more about give you a flavor for that Gibbs sampler. So each of these blue lines was a particular iteration. This separates out various iterations, and you can see, for instance, that we started out with kind of not too much of a dip here, and then we get a dip there, and maybe the bump here is a little bit bigger than the bump was here. So things are moving around a little bit, but there's a lot of information in this data, and so these density estimates don't vary wildly through our MCMC. You could do this with more complicated data. Here is with a mixture of 100 components. And what you can see here is that the individual densities move around a bit. This figure and this figure, I think, look qualitatively a bit different, also a bit different than that. Okay, so there are some tweaks, and one of the challenges is dealing with the number of clusters, and this slide talks a little bit about dealing with the number of clusters. A challenge with this model is that it rarely increases the number of clusters. And this can be solved in a number of different ways. They talk about reverse jump Monte Carlo and stuff like that unfortunately we're not going to cover in this class. But I think for the purpose of, if the goal was come up with a flexible density model for this pretty weird set of data, I think we did that pretty darn well. I recognize I moved through the code pretty quickly, but if you want to dig a little bit deeper, that code is there. You can run it right on Liberator and see for yourself how it all works. All right, so that is it for density estimation. The next lecture will talk about clustering. So